right, y'all. So this is the first lecture on the topic of waves, our next unit in physics. We started with unit conversion in units, and then we got into energy. Our next topic is going to be waves, and some of the stuff is things you might have seen before in junior high. But like everything else I'm going to do this year, we started with energy because I'm going to frame everything, and we're going to look at everything in the rest of physics through the lens of energy. That is the foundation of science. And so I want to define waves as simply a wiggle that transports energy from one place in the universe to another. And that's really about as basic as it gets. Normally when we talk about energy changing types, that's a transformation of energy, and that was the last unit. But if we're talking about one type of energy that is simply moving from one place to another, we're going to call that a wave. The wiggle is the important part. It's a back and forth vibration. So sometimes the vibration will move up and down like this. Sometimes it'll move left and right like that. Sometimes it'll even do some sort of circular thing. It's a repeated oscillatory, that's a fancy word for back and forth wiggle motion. There's a whole bunch of different types of waves out there. Lots is the technical term right there. But the reason that we want to do this, the reason that we want to talk about waves, the reason that we want to learn about this is that the two most important senses that you humans have, the ability to see things and the ability to hear things, the way that you navigate your way through this world involves you sensing waves. Your vision is simply just you perceiving and processing light waves that enter your eyes, and hearing is you perceiving and processing sound waves that enter into your ears. And so since such a huge part of our world is based on us being able to process these two major important types of waves, it's important that we kind of understand a little bit of the physics behind it. So there are two ways that we're going to go about categorizing waves. When we say it's this type of wave or that type of wave, the first way that we're going to categorize this is by the shape that the wave makes. And what I mean by this is, does the direction of the wiggle, does the direction that the particle's moving back and forth match the direction that the wave is actually moving? And so the first type of this wave shape is known as a transverse wave. And we see this all the time. Oops. Show wave as rope. This is you wiggling a slinky or a rope up and down. This is you shaking the end of an extension cord or a string. And you can see that these green peaks and valleys of this wave are moving to the right. So they're moving left and right. But those little reddish dots right there are representing molecules in the rope. They're just moving up and down. And so the idea that I want you to see here is that the energy of the wave, these pulses, these high peaks and low valleys, that's moving from one end of the screen to the other, but the individual particles of the material, the little atoms there, they're just moving up and down. They don't get permanently moved to a new location. So when the direction that the wiggle is perpendicular to the direction of the movement of the wave, in other words, the person moves their hand up and down like this, but the direction of the wave goes that way, when it's perpendicular, we refer to this as a transverse wave. And trans, of course, means cross or at opposite directions to each other. There's some key features here to this, and some of this might be anatomy that you all learned about in junior high school. We're going to call the top of all of the waves crests. So there's a crest, there's a crest, there's a crest. That's just another way for the highest point that the wave makes. And then the bottom of this thing is going to be known as a trough. Pigs eat food from a trough, I guess. That's one way to think of it, kind of a little valley at the bottom. The equilibrium or unwiggled position would be where this thing would be if it weren't stretched or displaced or wiggled at all. So if I was just holding the rope still, we would kind of mark an imaginary line right there saying this is the equilibrium position. Two measurements that we would make about this wave, if we were going to describe how big it is, you would first want to talk about the size of the wave relative to the equilibrium position. So you might say something like, oh, that water wave was 3 feet tall, or oh, that's just like a 2-inch ripple in the pond, that's not much. What you're describing when you say the height of a wave is how far above the normal position it gets, and we call that amplitude. You could also describe it as being underneath. Usually these waves are symmetrical, so if the crest is 3 meters above the equilibrium position, the trough would be 3 meters below. You don't measure from the crest all the way down to the trough, though. You don't do the total height. It's the distance above the unwiggled or equilibrium position. So that's one way you would describe how big this thing is the height of it. The other way you would describe the size of a wave is the length of this thing. And the length of the wave creatively enough, is known as wavelength. And that is the distance that the wave is long horizontally. And you can either measure from one crest to one crest, you can measure from a trough to a trough, you can measure from a upwards equilibrium crossing to another upwards equilibrium crossing. It's one full wave. And the thing to keep in mind is that a wave has an up and a down. So you could say that's one full wave. Or if you want to draw it upside down, that's one full wave. It's got an up part and a down part. So the first type of the shape, oops, I forgot to have the G's there. The first wave shape we talked about was transverse, and that's the one where the direction of the movement and the direction of the wiggle are perpendicular to each other. The other one is going to be known as longitudinal. Sometimes you'll see this known as a compressional wave, and in this case, the hand or whatever's causing the wiggle is moving back and forth, and the wave's moving in that same direction as well. And again, it's not a permanent displacement. The particles themselves are wiggling back and forth in place. And so if we come back and look at the simulation again, here would be a representation of a bunch of air molecules undergoing a compressional or longitudinal wave. So you can kind of see there's these bunched up spots that are moving to the right here. The higher density areas are moving to the right. But again, we look at our just 3 random particles that they've colored with this kind of purplish color, and they're just moving back and forth. And if I bunch this up a little bit tighter, we can kind of see the bunched up areas moving to the right. Think of those like the crests, right? And the kind of spaced out areas that aren't as dense, we think of those as troughs. And so they've got a special name though. Up on the top here with this type, we could say, well, that's a crest and that's a trough. What we're going to do down here for longitudinal wave is say the spots that are really compressed, the spots that have a really high density like this are known as compressions. And then, let's see, here would be another compression over here. The spots that are more spaced out, though, you'd say that, oh, that's weird, you'd say that they are rarefacted. And that's just another word for saying that it's more spread out, that the rarefacted areas have less particle density. So I kind of think of rarefactions corresponding with the empty spots, compressions corresponding with like the really, really dense spot. So the first way we're going to describe, and if we were going to talk about the size of this wave, the wavelength of this thing, you would just measure from one compression to the next one. That's one full wave right there. Just like up here, we would measure from one trough to the other and call that a full wave. So we can talk about waves either being perpendicular to their motion and their wiggle or parallel to their motion and their wiggle. This one right here, this would be an example of the wave in the stadium. So, you know, you guys go to sporting events, well, we used to before the pandemic, and sometimes like the people would want to do the wave. Well, the wave moves around the stadium. It moves, you know, left and right, but the people stand up and sit back down. That's the wave. This right here, the compressional one, would be a lot more like telephone, where, you know, that game we played in elementary school where you would lean over to your right and listen, and then lean to your left and whisper into the person's ear. The signal, the telephone phrase went around the room and your little heads bobbed back and forth left and right. So the first way that we're going to describe waves is the shape. The second way that we're going to describe waves is whether or not they require a medium. And a medium is just a fancy word for the stuff that gets wiggled. So if a slinky is having a wave pass through it, we would say the slinky is the medium. Ocean waves, the water is the medium. Earthquake waves, the earth is the medium. Sound waves, the air is the medium. It's the stuff that actually gets wiggled. What are the molecules that are vibrating back and forth? Why they have to use a fancy word like this, I don't know. They just do. I would have called it material or something. So the first way we would describe the waves, what shape does it make? The second way we describe waves is whether or not they need a medium. And there's this group of waves known as electromagnetic waves that don't. So these are all different types of light or radiation, things like microwaves, ultraviolet or UV, X-rays, infrared or IR, visible light, radio. All of these types right here, sometimes known as radiation, but just different types of light, are a special group that don't need a medium. So light can go through the emptiness of outer space. It's true that the sun gets its light all the way from the sun to us. It goes through a vacuum of space. You don't need any air for this to work. Every other type of wave that we're going to care about that does need a medium is going to be known as what's called a mechanical wave. So we're going to split waves up into either compressional or transverse, and we're going to split waves up either into mechanical or electromagnetic. This is the unit that we're going to study for the next couple weeks. This is going to be unit 4. This is what we're going to do later. So for the next couple weeks, these are the ones that we're going to care about, and these are the ones that we're going to process right here. So Every type of wave out there has both a shape categorization and a medium categorization. Geez, that's a big word. And so really there's four different types that are possible. We could have a transverse light wave, a compressional light wave, a transverse mechanical wave, and a compressional mechanical wave. What we're going to spend the next couple weeks going over is these two right here. All right, so y'all have got a little concept builder to make sure that you understand what's going on with these different distinctions and your simple definitions and stuff, and we'll come back next time with a couple more examples of what happens when waves do things like see a new medium or run into each other or bounce off of a wall or something. All right.